Okay. So yeah, a little bit. We'll end up with the Erlang ecosystem where we're talking about different languages and implementing languages on top of that, and why we'd want to do that. I just want to very quickly go through and try and explain why things look like they do in the system. Okay. How Erlang looks is very specific, and there's a reason for most of the stuff. And originally, when we were working at Ericsson, we had this. One of the problems we had in the computer science lab where I was working was to how we could improve programming and maintenance of telecom systems. So Ericsson had the AXE system. It was a very successful product, but it was difficult to develop and maintain. So we will try and look at the problem of how we could improve that. And one of the things we found out was the telecoms part was not the actual problem. Controlling the switch, someone else had done all that work. We didn't have to do that. There were other problems we had to attack. And this was basically a list of these. They come from our boss at the lab there, Bjarne Dekker, in his thesis for it. And these were the actual problems. This was where the problem really was. And if you look at these, some are more interesting than others, right? We had concurrency, a lot of concurrency going on in the system. We had to have a system which can handle a lot of concurrency. We had timing constraints. Things had to happen in a certain time or not take longer than a certain time. We needed distribution for fault tolerance. We needed to be able to build upgradable systems so we could upgrade the system while the system is running. And we had a lot of demands for fault tolerance in the sense that when things go wrong, the system must be able to handle that, clean up afterwards and keep going and never crash. So while we say the Erlang philosophy is let it crash, what we mean is the system should never crash. And what we found was that anything we did that to be interesting had to be able to solve these problems. If it couldn't do that, it wasn't interesting. Right? However fantastic it might be, it had to be able to solve these problems. And what we found later, of course, was if you look at through these issues, there is absolutely nothing about telecoms in there. So these problems, these issues, the things we had to solve are much more general than telecoms. And what happened was that Erlang and the system around it developed to solve these problems. Okay, that's what we're after doing for it. And what you find is Erlang, the language, and OTP, the system on top of it, provides direct support for all these things. This is why. And so some reflections from this, while we're working on this, we found that we were not out to implement a functional language. Okay? It became functional along the way. Now, whether from your functional point of view that's good or bad, I don't know, but that's what happened. Right? We originally started off as Prolog and it ended up being a functional language. We were not out to implement the actor model. Okay? We did not know about the actor model. We found out about the actor model later when we read papers saying that Erlang implemented the actor model. We did not know about this, right? This was our way of making a solution to the problem. And we ended up something pretty close to the actor model for it. And the base was this, we're just trying to solve the problem. That's really what all we were trying to do, is solve the problem. And we felt this was the best way of solving the problem. So where did we end up? Lots of lightweight concurrency. Concurrency was so important, it's basic, built into the language. It's so important, it's not something you put a library on top, it has to be a part of the language at the very low level. Same thing with process isolation. Same thing there, processes are going to die, we have to make sure they don't affect things adversely for it. Asynchronous communication. But primitives for error handling. Again, this was something we decided was so fundamental to the problem, it's not something you put on top as a library, you build it into the basic system at the very low level for it. Continuous evolution of the system, code upgrades, yes. There is support in the system for doing soft real-timeness and making sure the system doesn't block. We had a few other things as well too we wanted a high-level language. Remember, this is 30 years ago, so high-level then was a bit different from high-level now, but we wanted that. We also wanted something that was basically very simple. The base language, the base system, the idea should be very simple. If you have a simple base, you can build anything on top of it. If you have a very complex base, that makes everything complex. That makes an awful lot of effort into it. You want the base to be very simple. Simplicity is not simple, right? Basically. If you look at Dijkstra, he says simplicity is difficult. That's hard to do it, hard to appreciate it, and often complexity sells better. But if you want to build a system, what should be simple at the base? And we also found out, related to this, provide tools, not solutions. You want to provide tools so users can build their solutions, not try and guess what they want and provide solutions for them. You usually get it wrong. Right? So where did we end up? The language, it's a simple functional language. If you look at the Erlang functional language, it's a simple functional language, and all the things you'll find in it, you'll find in most other functional languages as well. There's nothing really strange about this. We've got support immutable data, immutable variables, pattern matching, etc., etc. for it. It's dynamically typed, and we don't have user-defined data types. Concurrency. So where do we end up? Concurrency is very simple. It's isolated processes. It's asynchronous sending messages and a selective receive of messages. That is the concurrency model. That's it. There are a few other things on top, but these 3 points are the basic ones for it. That's about as simple as we can get it. And with that, you can build whatever you want to on top. We don't do global data. We don't do mutable, we don't do shared, and we don't do global. That's it, right? That just makes everything else extremely difficult. Global data makes scaling difficult. Removing global data simplifies scaling. So what about that's the concurrency model. The error handling model, yeah, errors will always occur. That's the basic principle for it. Get over that fact. Accept it and get over it and work with it. Right. There, sorry, yes, look at the wrong one. That's the basic premise for it. And the basic goals, what we wanted to, of course, is the system must never go down. That's the worst thing that can happen. So parts might crash and burn, you might get errors, but the system as a whole must be able to detect that and keep going. We also wanted to avoid writing error checking code. If you've seriously written error checking code, that's a lot of effort and extremely easy to get it wrong. So how could we make a system where in most cases we did not have to check for errors, right? We just wanted to let things crash. So when something goes wrong in the system, we'll let it crash, and someone else will clean up afterwards. So this enormous cleanup service around us which will handle things going wrong, we just let things crash. So how do you build robust systems? Well, there are two things you need, at least two things you need to do. You need to make certain that some things are always available. If that thing is not available, we can't say the system's running. And also what you need to do is when things crash, you need to be able to clean up afterwards. So you can keep on going. And that's what the error handling does for it. Getting very close here now. OTP on top of Erlang is a library that incorporates a lot of these ideas and helps you build systems using these ideas. So the Erlang provides a lot of primitives, and OTP uses those primitives to help you build these type of systems. So you don't have to use OTP, but you have a lot of support in there for building these type of things for it. But the basic primitives are in Erlang, and the connection between Erlang and OTP is very tight. And the thing to remember here, irrespective of the name, there's nothing about telecoms and OTP. I think the closest the existing system is an ASN.1 compiler, which is used for protocols, but that's nothing telecoms.
And the T.
Sorry?
And the T.
And the T, yes, yes, yes. It was a politically correct name in a telecoms company, right? There's nothing telecoms. You can try and rationalize afterwards. So that's going upwards from Erlang. Now just very quickly going down here, right? So we have the beam. What is the beam? And it's a virtual machine to run Erlang, and that says nothing and it says everything. What does the beam do? It runs Erlang. And that means everything in Erlang has support in the beam. So in the beam we have support for the concurrency. We have support for the process isolation. We have support for the error handling, the continuous evolution, the code handling, support for that. All the soft real-timeness, the fact that the system will never block, there's support for that inside the beam. It has a lot of support, for example, for doing a transparent multi-core. You run on your system, will grab every core it can have and use it, right? There's support for doing that automatically for it. There are powerful introspection tools as well, and interfaces the outside world. So Erlang and OTP are very closely connected, and Erlang and the Beam are very closely connected. What does the Beam do? It runs Erlang. That's it. Right? Everything you'll find in Erlang, you'll find support for in the Beam. And a few other things as well, which aren't system things like immutable data, predefined set data types, and stuff like that for it, the functional support for it. The data immutability goes all the way down deep inside the Beam. It's practically impossible to put mutable data in the system. And there's no guarantees that even if you manage to do it, it'll work. Right? It will probably crash the system along the way. So these type of things for it. So if you're running on the Beam, you're getting Erlang for it. And that's what gives us the Erlang ecosystem here. What we mean by the Erlang ecosystem, you have this concept, you have the Beam, you have the Erlang OTP on top of that, and then you have a set of languages implemented on top of that. So we have currently, for some of them, these vary, some of them anyway. We have currently, for example, Erlang, of course, Elixir, LFE, Prolog, we have Allure. We have a number of other languages that are being developed and working on. But they're all part of the same ecosystem. They all get all these features from the Beam and from OTP. They get them for free. And if they've done it correctly, they can all interact with each other and use features from them. So I write in one of them, I can access the things from the other ones very simply for it. And yeah, that gets us a bit onto extending the system. So turn this one off. No,
okay, so as Francesco told today in the morning, the first attempt to build one language on top of the Beam was RIA, like almost 10 years ago. And it was the first time I saw that Erlang, the language, was like a DSL for the Beam, and you could take the syntax and build upon the virtual machine itself. And after that, many people started seeing this. And so you have the Beam, Erlang, and OTP, and you can build your language on top of either directly on the Beam or on top of Erlang. And we will explore the languages that, some of them, because there are many, but some of them and how they relate and how they are different and which parts do they take in from the ecosystem. So we split here the languages between what we call native languages, which are languages that take advantage of the properties of the Beam and don't have a significant overhead. They are not trying to emulate anything. They don't have a big runtime system. They are taking advantage of the properties of the Beam. I can draw a comparison between like porting one language to the JVM, like Jython or JRuby, and building one language with influences from other languages, taking advantage of the properties of the JVM, for example, Scala and Clojure, which are like ML inspired for the JVM and Lisp inspired for the JVM. In the case of .NET, you have F#, which is like an ML for taking advantage of the properties of the virtual machine. Here we will explore some of them. I guess I don't have to introduce you to Elixir, but we will cover you lightly how it's implemented, but it has its own conferences, so yeah, there's a lot of content regarding Elixir. We will cover LFE, which is a Lisp-flavored language developed by Robert. Efene, which is developed by me. And others, Clojure, which is in development, and Alpaca, and also Lure. These are the native ones, sorry. These are the native ones we want to cover. And then we will cover other ones that are ports of existing languages to the Beam. And we will see how the mismatch between the semantics of those languages and the Beam make them different in some sense. So the first and the biggest language is Elixir, which I will read the summary. It's a dynamic functional language designed for building scalable and maintainable applications. It's deeply influenced by Ruby, but it's not Ruby. It's not Ruby on the JVM. It doesn't try to. In this sense, it's a native language. It says, OK, we like Ruby, we like ideas from Ruby, but we understand that the Ruby virtual machine is not the Beam and that they are different. One is deeply mutable and the other is deeply immutable. So if you want to port the Ruby to the Erlang virtual machine, you will suffer pain. And people will complain that, yeah, it's like Ruby, but it's not 100% Ruby and it's slow or different things. It has metaprogramming capabilities using macros. This is like an influence from Lisp, I guess. And there's, I was talking about this this morning. Like Erlang, it was the first and developed many ideas. And over time, it got like inconsistencies. Because something was needed and one decision was taken, then some new decision was inconsistent, some APIs are different, some parts of this problem space are covered because Erlang came from Ericsson and from that background. So Elixir had the chance to make a complete design from scratch from one language, taking advantage of all the things learned in Erlang in 25 years, but also on all the things that were learned on other communities like the Ruby community over 10, 15 years that Ruby existed. It has its own set of tools because at the point when Elixir started, the tooling around Erlang wasn't that good. So it's nice that there's this feedback cycle where Elixir built Mix and Hex, and the Erlang community took Hex, and we already had Rebar, so we made Rebar 3, which is really similar to Mix. So there is this back and forth between the communities which you talked about today, which is really useful and interesting. But it has the same semantics of Erlang, because if you want to make a production-ready language on top of the Beam, you have to take advantage of the properties. If you fight against the virtual machine, you will have problems. Another example of this, for example, there's a port of closure to the JavaScript called closure script. They had a problem. There are no integers in JavaScript. There are only floating point 64-bit floating points. So they either had to wrap the integers, which will mean it will be slower and the interoperability with JavaScript will be hard, or they could say, okay, if you're doing numbers on closure script, it plays to the strengths of the JavaScript virtual machine. If you are doing numbers on the JVM, it will be numbers on the JVM. So they took that decision so that closure script was faster and would interoperate better with the virtual machine it was running on. So yeah, I ended up explaining a lot of Elixir. It was going to be a summary. So I guess you could explain LFE?
Yeah.
It's your language after all.
Okay, so yeah, LFE is Lisp flavored Erlang. It's a Lisp syntax front end to Erlang, basically. Having all the benefits of the Lisp syntax. If you don't love Lisp, you've missed something in your life, right? It's actually the easiest, the simplest syntax you will find in any language. Everything's a list. The first thing tells you what it is, and the rest is a list of arguments. And that is Lisp syntax, right? In one line, that's it, right? And LFE uses that. And it's truly homoiconic. It has macros in the same way as Lisp does, which are extremely simple and at the same time being extremely powerful. Macros as God intended. But the interface to the Erlang system is very tight. And again, it's the same decision was made there as in Elixir. We will adapt the language to the Beam, to Erlang. So there are some things, it's influenced by, say, Common Lisp or Scheme, but some things from those two languages just don't work without a lot of effort, so we just don't do it. We don't have mutable data, for example. That's just it. We accept Erlang-style modules and functions, which are slightly different from what standard Lisp give you. We have macros. Unfortunately, they're only compile time. There is no support for macros in the virtual machine, so we can do them, but they're mainly compile time. I had a really smart hack that tried to do them at runtime, which sort of worked, but it still evaluated all the arguments, which macros shouldn't do. It's a Lisp 2 instead of a Lisp 1. If anyone wants to take this discussion, I'll take that later, if you don't know what it means for. So, yeah.
Okay, so that's the answer why LFE is not Common Lisp on the Beam, because the same reason why Elixir is not Ruby on the Beam. And here you will hear why Efene is not Python on the Beam. So many years ago, I already forgot, I had this the same realization that the Elixir community had regarding Erlang being a really useful tool an ecosystem of a set of tools and libraries and language to build solutions to problems that were coming, which were scalability, IoT, web services, message queues, databases. So I was seeing this great tool and nobody using it. And one of my theories was the one that was explored in the previous talk, which is people usually like to things that are similar to what they already know. We usually make really short assessment of new things and compare them to the things we already know. So you say, well, what's that syntax? And you say, OK, Go is similar to what I already know. Let's switch to Go. You don't do a really deep assessment of the virtual machines and the properties and the semantics. You say, yeah, I can learn the Go syntax in 1 day. And the Erlang syntax, I would take me like a week. Not even thinking that you may have to use that language for 20 years. You want to learn the syntax in 1 day and not 5 days. But for those reasons, I say, OK, let's make it like this. Let's make a Python syntactic sugar on top of the Beam, keeping as close to Erlang as possible. So the idea was to remove one of the excuses for why people won't try to learn Erlang or a language on the Beam. So it's deeply inspired in Python. Almost everything is inspired in Python. Of course, Python doesn't have multi-clause functions and doesn't have pattern matching, so you have to improvise a little bit, and has some inspiration on JavaScript also. I call it an Erlang dialect. It's not even a language on its own, because it doesn't have any semantic that Erlang doesn't have. So it's like CoffeeScript to JavaScript, basically. Makes use of all the Erlang tooling, all the libraries. There's no standard library in Efene. But we recognize that people like to have quick answers to the things. If I had to write a web server or web application on Erlang, what should I use? And they Google how to build a website with Erlang. And they don't have to go hunting on GitHub and assembling a set of tools custom to their problem. And then when they make a question on a forum, they say, yeah, I'm using Cowboy, but I'm using this JavaScript JSON parser, but this logging library. And the other guy say, look, I use this other log library and this other JSON parser, so I cannot answer your question. In this case, Elixir, they define the stack themselves. In my case, I don't have a big community and not much time. I cannot build the stack. And since Efene is so close to Erlang, I just pick a set of solutions. It doesn't mean you cannot try others, but all the tutorials, all the documentations will assume this set of tools. And whenever you start with something, there's this list, and you say, OK, I need this, I need this, I need this I don't need, and you're ready to go. It compiles to the Beam bytecode when you're compiling by default, but since it's one-to-one to Erlang, you can compile to Erlang source code also, which is possible in many languages. But what I mean here is, like, the Erlang emitted is one-to-one. It's not really hard to follow. It's the same. You may have one line split into two, but the code will be really readable. It will look like you wrote that code, or some human wrote that code. It's stable. It's 1.0 for like almost 2 years. But I'm using the Rust style. I'm writing my stuff, my work stuff in Efene for over a year and more, and tools before that, because I wanted the first release to be production ready and tested. And if there's a bug, I will know, because my product will not work. If you want to try it, I never announced the 1.0 version outside of talks in Erlang conferences. This one is really interesting, Clojure, which is a almost straight port from Clojure to the Beam. The interesting thing is that this is the only language that is a direct port of another language that tries to not have overhead, because the Prolog port and the Lua port that we'll cover later are straight ports of existing languages, but they have overhead. Clojure tries to port a language that already exists. The cool thing is that it's already immutable and functional, which makes it easy. But Clojure, being a Lisp designed for the JVM, takes advantage of some of the mutability properties of the JVM. And those cases have to be solved in some way. they may be solved either with some slight overhead, or in the case of ClojureScript, where you say, OK, numbers are a little bit different. For example, integers in the Beam are promote to big integers without you doing anything. In the JVM, you have the big int and you have the integers. So that will be different. I don't think it will be a problem, because if you're overflowing on your Clojure code, then you will have two different bugs, but two bugs nonetheless. And this one is also interesting in another sense, Alpaca, which is an attempt to have an M. It was previously called ML-flavored Erlang, following the pattern that Robert started. It was renamed to Alpaca. The interesting fact about this one is that it's the only one that tries to add a statically typed language to the Beam. It's ML inspired, but it's not a port of any language, and it's really interesting. You should check it out. And this is the description: statically typed, strict, eagerly evaluated functional programming language for the Beam, relies on type inference, but does provide a way to add type specifications like Hindley-Milner, like Haskell, where it will get almost all the types. Whenever there's a problem, you add the types to make the compiler happy. And now we have the non-native languages, which the two are from Robert, so he will cover them.
OK, yeah. So the problem here is with the other languages, with the ones we've seen so far, we've been willing to adapt the language to fit on top of Erlang in the Beam. To get the most efficiency you can get out of the Beam, you're basically running Erlang, so we're adapting the languages to do that. And we're accepting the fact that we'll have to make changes from where the languages come from. Okay. That's a choice that was made in all these cases to get the maximum speed out of it. These other ones, which we call non-native, we've gone the other way and said, OK, we are going to implement the language exactly as it is defined. And we'll take any blow that comes for that, because we want the language to be exactly defined here. And we have two examples here. I've done them both. There are probably more. OK, I'm not saying anything. So Lua is, well, Lua is a powerful, efficient, lightweight, embeddable scripting language that supports procedural programming, object-oriented programming, functional programming, data-driven programming, and data description. I don't know what it doesn't support, OK? It actually does if you start looking inside it. But so the problem here is that Lua implements Lua 5.2, almost the whole description of it, the whole thing. There are a few small things it does not do. But Lua supports shared mutable global data, which are definitely the things we don't do, right, in Erlang. The way Lua handles code does not map into how Erlang handles code. So in all those cases, we've been forced to interpret the language on top of Erlang to make it fit, to make it work like Lua does. So yeah, Lua has shared global mutable data, because we're implementing that and we're passing state around doing things like this for it. And that is definitely a cost. That is definitely a cost, but it's one we're willing to take because we wanted to make it compatible with Lua. So it's a choice you make, right? In this case, we're willing to pay that cost to do that because that's what part of the problem was for it. It's the same thing with Erlang. So Erlang is an implementation of Prolog, and Prolog does not have the same semantics as Erlang, right? And again, it's difficult to directly map it over, but we're willing to pay that cost. And it's the same thing with data. So a lot of Prolog's data maps directly onto Erlang data, not surprisingly, seeing where Erlang comes from, but there are a couple of things that don't do that. There is no natural way in Erlang to implement Prolog databases. You have to do it in some way yourself, and the same with logical variables. So we're actually interpreting Prolog on top of this to get these features in. And here again, we've made the decision, we have a definition of Prolog, this is what we're going to implement. And we'll take that blow to do it, because that's what we want to do. And this is what we mean by non-native languages for it. And yeah, they are slower, but again, it's what you're after for it. And I'm guessing there are probably more languages that do this, but I haven't really seen them working for it. But again, so we've got these two ways of going here, two branches. Either you say, we'll take a language and we'll adapt it so it fits on top and runs very efficiently, or we'll say, no, we'll keep the definition as it is, and we'll accept the fact it's less efficient. These two. You have to make a choice, basically. And yeah, we have a bit of table of data here for it.
We will do a fast comparison. I just noticed, like the first Erlang prototype was implemented in Prolog.
Yeah.
And Erlang got the syntax from Prolog, and now you are doing a Prolog in Erlang.
Yeah, so I can almost run the existing Erlang implementations written in Prolog on top of my Prolog. Basically, the only thing I need to do is to be able to define operators. I just haven't added that. If I could do that, I could take the old Prolog versions back and run it on top. And yeah, it'd be interesting to try that.
Full circle.
Full circle, yeah. Then I can implement the original Erlang compiler written in Prolog on top of that, and we can go forward and come back again. Yes.
Like Inception.
Yeah.
Slower and slower as you
getting slower every level down. Yeah.
So here is a table where we try to compare the languages, define some categories. We already covered some, so I will go fast. And because, well, we have time. OK, I don't know if that clock is right.
That clock's Stockholm, right? So
OK.
Yeah, we've got a lot of time. We've got 8 hours left, so there's no problem here. We can do this.
I will go fast, and we may cover it after in the questions. So Alpaca, the main influences are OCaml and Elm. For Clojure, it's not an influence, it's Clojure. Efene, mainly Python, some JavaScript. LFE, Common Lisp and Scheme. Erlang is Prolog, and Lua is Lua. Elixir is the first stage when you are compiling a language. The first stage is you take a text file and you split it into small tokens, as a list, a sequence of tokens with the variable names, the numbers, the commas, and stuff like that. There's one Elixir library in the Erlang standard library, which is the Elixir that Erlang uses. So all of them use that one because it works. And it's another language or small language developed by Robert. And the only one that is different, and it's different in the next one, is Clojure, because the Lisps usually, and Clojure in particular, have a reader, and they can read metadata, or they have like a way to change the meaning of things at read time. So Clojure implements a handwritten Elixir and parser. The parser is the next stage, which is you get this list of tokens and build what's called an abstract syntax tree, or a tree that's a data structure that represents the logic of your code. And for that, there's also a library developed on the standard. There's a library for parsing in the standard library of Erlang called Yek, which is inspired by Yak, which is yet another C.
Yet another compiler.
Yet another compiler.
Yes.
This is the Erlang version of that. So Alpaca and Efene use that one. Clojure uses the unwritten version because of what I explained. Erlang is handwritten, and World uses Yek also. And you can explain why LFE uses something called spell one.
OK, so the problem with Yek is it needs to know exactly the right number of tokens to do something. If it gets too few tokens, it bombs out. If it gets too many tokens, it bombs out. And it's just the way that the Yak compilers work. It's an LA-LA1 parser. That's just the way they work, right? And that does not work for Lisp, because you don't know, for example, which right parentheses ends an expression. You have to keep count of them. So there's no defined way of doing that. That's why Yek did not work. Spell is actually an LL1 parser generator I wrote, which can do that. That's why I did that for it. And inside that, then the Lisp syntax becomes very concise. And Prologs has to be handwritten because the Prolog parser includes backtracking. You can literally parse something and not know until you get to the end which choices you're going to make and how you're going to parse the thing, right? So you need backtracking in it, and none of the parser generators do that for you. It's quite simple to write, but you have to do it.
So the next stage is, after you have your tree representing your program, you have to compile it to something. The lowest level solution would be to compile straight from your tree to Beam bytecode. but you can reuse a lot of the infrastructure already in the Erlang standard library because the Erlang compiler is written in Erlang, and all the things that it uses are in the standard library. So you can just hook into the level you want, and depending on the level you compile to, you get to use the tools that Erlang uses. So usually there are two targets, core Erlang, which is a simplified functional language that is an intermediate language where almost all the optimizations on the Erlang compiler happen. And there's a higher level one, which is the Erlang abstract syntax tree, which is what the Erlang compiler generates when it's parsing source code. So if you hook to the Erlang AST, you get the benefit of being able to compile to Erlang source code and being able to use all the tools that work with Erlang source code. For example, xref, which checks for references to functions that don't exist, and also spec also works at the AST level, and the warnings for unused functions and all the warnings that Erlang checks, you get them for free. You can compile to the lower level core Erlang, which is a nicer functional language, and you can do things like introduce different scoping rules, I think. Yeah. Because you're on a lower level. You're not compiling to an Erlang representation of your code, but to a different, simpler functional language. And in the case of the non-native ones, you have to compile to some intermediate representation and have an interpreter at runtime that will interpret that representation. So whenever we write code in these languages, how do we call to code from those languages from Erlang? So I'm writing some Erlang code, and there's a library implemented in Alpaca. How do I call to that code, to that function? In Alpaca, which I think it's similar to how Elixir does it, Alpaca compiles all the modules into modules prefixed with alpaca _. In Elixir, I think it's elixir dot, elixir with uppercase. So you just do that, and you have to be careful because in Alpaca, all the type checking is done at the compile time. At runtime, there's no code checking for the types. So if you send some weird types, it will crash with weird errors because it's not expecting that. Enclosure is just a plain call. You just prefix it with the Erlang namespace. In Efene, it's a plain call. You cannot even know if you're calling an Efene or an Erlang module. In LFE also, it's the same. In Erlog and Luerl, since they are like sandboxed, you need to implement a specific module with a specific interface. Yep. That's right. Yeah. If you're writing code in one of these languages and want to call to code that's written in Erlang, like the other way around, in Alpaca you have to use an foreign function interface module because you have to write the types of that Erlang function. Because the Erlang function doesn't have types, and Alpaca needs to know the types, you have to write them there. Enclosure is a plain call, Efene2, in LFE also. And in Erlog and Luerl, you have to write a special Erlang module.
Yeah, you have to write an interface module, which you then call from those languages, which then translate the call into an Erlang call. There's no direct way to do it.
As Robert said, the Erlang doesn't support creating custom data types, at least not as first class. So if you're implementing a language that's really close to the Beam and to Erlang, then you don't have any problem. Lists are lists, and tuples are tuples, and numbers are numbers. But if you're trying to do something different, a common strategy for some of them is to wrap them in some way and detect that structure and know that that's an abstract data type. Alpaca supports all the native types from Erlang and has a wrapped, it wraps the types that you create in Alpaca. In Clojure, all the types are wrapped because Clojure defines protocols, so everything can be a sequence and stuff like that. Efene doesn't define any new data type, LFE either. Erlog and Luerl define some, like logical variables and the Erlog database, I think it's there. And Luerl tables are not maps because they have different semantics, so Robert had to create known data type for that. In terms of overhead, how much overhead, like if I write some algorithm in Erlang and in one of these languages, how much overhead do I get? None in Alpaca. In Clojure, only dispatching to protocols. So if you do list.map in Erlang and you map over a sequence on Clojure, you will pay the price of dispatching on the protocol, which is like one extra indirection and some extra overhead. There's no overhead in Efene, no overhead in LFE, and Erlang and Lua are interpreted, so the price of the interpretation. And the last one is runtime. You can have, like, your language can either do everything at compile time, and everything is compiled to bytecoding modules, or it can also have a runtime component that does some extra stuff that you cannot do at compile time. Alpaca doesn't have a runtime component. Clojure has the loaded namespaces, because namespaces in Clojure are like mutable and kind of interactive. You can explore them and add stuff and replace stuff, so they are kept in ETS tables. Efene has no runtime, LFE no, except you're using an extension called flavors. Yeah. I don't know if you want to cover it.
I'm not going to. Anyone wants to know about flavors, come by. It's objects done properly, right? For it.
And Erlang and Lua don't have any runtime component. And how much time? Yeah. OK, this is the last slide, actually.
The last one, yes.
Yeah. So what happens if I want to extend Erlang, but not in a language? There's no way I can build a language on the Beam that will solve my problem. How can I still be in the Erlang ecosystem? There are some alternatives. External ports and linked-in drivers is like a standard interface that allows the Erlang and the Beam to interact with external systems in a standardized way that looks like you write and you read things. NIFs, which are simpler, they run the code C or binary, native binary, inside the virtual machine. It runs really fast. The problem is that if it sec faults, it crashes your virtual machine, so you have to be careful. You can write C nodes, which is a C library that allows you to write something in C or in something that compiles to C that from the Erlang side looks like an Erlang node. So you send a message and you receive messages, and you can monitor it and all the things you can do with the Erlang node. And on top of that, some people wrote a bridge to Python. There's also JInterface, which is like a C node, but for the JVM. You talk to the JVM like it's an Erlang node. And finally, there are two interesting things that I think we should work more on, which is write C nodes and NIFs in Rust, which means they are more approachable than C, same speed, and they don't sec fault, or they should not sec fault. And the next one is WebAssembly. The problem with some of these, with NIFs and C nodes, is that you have to, like, if somebody downloads your project and wants to make use of this, they have to have the compiler toolchain to compile that C code to the native code. And then when you ship it to some other computer, if the architecture of the other computer doesn't match where you compiled it, it won't work. WebAssembly is like a architecture independent and safe binary. So you can ship the compiled WebAssembly file in your project, and the users of your code don't have to have a compiler toolchain, and it will run on every platform that WebAssembly supports. And it will be fast, and it will be safer than binary because it has safety properties. And also, interestingly, we write on top of the work made by Google and Mozilla and all the others, optimizing WebAssembly and defining it, and we can just use it without problem. So this was all, and I don't know if we have time for questions.
We don't have time for questions, but I'm sure you guys can find it in the hallway out
there.
Thank
sure.
you so much.